Then I'd like to introduce to you Antigoni Polychroniadou, who you probably know, who is at JP Morgan AI Research and also a former Aarhus graduate. So we're happy to have her back, unfortunately only virtually this time, maybe in person next time. And she's going to talk about efficient MPC in the honest majority setting.
Thanks a lot, Karsten. It's kind of unfortunate that it's virtual, but I hope to see you all soon. But let me start because I think we're running out of time. Okay, so I'm going to talk about some of our recent works on honest majority MPC. And for some part of my talk, I also used the slides from Yifan. I think Yifan is already qualified to be speaker next year. So let me start. So our setting, we're in the information theoretic setting with arithmetic circuits and finite fields. And we are, like, as I said, in the honest majority setting. And we are achieving in our results both semi-honest security and malicious security, but this talk I'm going to focus only on semi-honest security. Okay, so why do we care about information theoretic protocols? I mean, they don't require any computational hard assumption. And because of that, the local calculations are very fast, almost linear. So basically the bottleneck there is the communication complexity. And this is where we're going to focus too in this talk. So we're going to focus on the communication complexity of these information theoretic protocols. Although if you have any question at any point, I don't know how we can do that, but ask Karsten. Maybe he can say the question, or we can have questions at the end. I don't know how it will work. Okay, so first, I'm going to start with the Damgård-Nielsen protocol. And if you don't know this protocol, maybe you should not be sitting there. I'm joking, but it's a very influential protocol. Many works are based on this protocol. And first, we're going to actually review this protocol. And just like for many years, there were no improvements on this protocol. There was this marginal improvement from 6 elements to 5.5 elements. And in this talk, we're going to show how we can reduce the DN complexity further. Okay, so what we're going to see is that from 6 elements, we're going to go down to 4 elements. And we also have a second protocol in which we can also reduce the round complexity by half. But in that case, from 6 elements, we go to 4.5 elements. You're going to see how we get these results. So it will be more clear later in the talk. Okay, and here is the picture with the comparison to the related work. By the way, we call this protocol Atlas. So here in the semi-honest setting, where we focus in the stock, as I was saying earlier, from 6 elements, we go to 4 elements. And if we want to also reduce the round complexity by half, we can have 4.5 elements. And the protocol, basically, in the malicious setting, we can achieve exactly the same complexity. So as you can see here, we have the same complexities. And these are the improvements over the previous works. Okay, so let's review the Damgård-Nielsen protocol. I'm going to go quickly over it. It uses some secret setting. You all know what is this. I'm not going to give any details. We just hide the secret in a single location. So this is the notation we're going to use for the talk. And with some secret setting, we can locally add shares, and we can also multiply. So if we multiply 2 shares, the degree rises. Okay, so these are the standard things. And let's see how the Damgård-Nielsen protocol works. As I said, when we multiply, the degree rises, and how we can accommodate for that. So it is assumed that we can have double shares, which we can have actually even before the inputs are decided. So assuming that we have sharings of some random value r of degree t and degree 2t. So what we can do, we can actually multiply the 2 shares and then add the random sharing of degree 2t. Okay, and then let's say we have a king like party P1. So everybody sends their shares of the masked result to the king, and then he can reconstruct. He has enough shares to reconstruct and get the answer. And then basically we can actually subtract. We send the answer in the clear to the parties, And the parties, since they also hold this double sharing, they can subtract the double sharing and indeed get the a sharing of the multiplication of the two numbers back to the original degree t. Okay, so this is the protocol, very simple and very simple actually to describe even. And here the only interaction is when we do this reconstruction to reduce the degree. Okay, so here there are first like two observations. The first is that instead of like for the king to send the value in the clear, he can actually send shares of those values. Okay, so we're going to do this modification first, which is very useful, and that was observed first in the work of Goyal. Okay, and this is, we can do that, right? Because we have like the random sharing of R, so then we can still like, instead of sending the value in the clear, we can actually keep operating on the shared values. Okay. So now, when the party is honest, and then we are sending, now we are operating on shares, okay? Then what can happen is that because P1, let's assume he is honest, okay? So he's getting and he's giving out like honest shares, right? So the corrupted parties are going to get only T uniform random shares. So from the result, they will not be able to tell actually what are the inputs. So privacy is preserved here. Okay, so given that P1 is honest, okay. Okay, so as I was saying, even if the adversary knows the shares, and even when we operate on the secret value, on the shared values, the parties cannot really break the security. Okay, so that was if P1 was honest, but P1 cannot be honest, right? So, and in that case, that can happen basically half of the times, right? So if we do a round robin fashion to send the shares to the single parties for the reconstruction, then for half of the multiplication gates will be handled actually by honest parties, okay? So in that case, half of the time P1 can be corrupted, okay? And this actually this observation allows us to do the following. So so we can have like these double sharings, okay, in a way that we don't need actually to generate a lot. So when P1 is honest, we don't really need to do that, to have the shares to be uniform, okay. And when P1 is corrupted, then what we can do, we can actually generate T-wise independent double shares, and that will be enough, okay. So basically, with this idea and this observation, if we can have the parties rotate in a round robin fashion and just generate T-wise independent double shares, and then we show how from T pairs we can go to N, just locally, then we can actually have half, we can use half of the elements. So now for the double shares, okay, because we can use this observation, we can reduce the number of elements that we need to exchange by half, okay, because when P1 is honest, as we observed above, we don't need them. We don't need them to be like uniform, okay. So this is the first observation. So we immediately go from 4 elements to 2 elements, and in the online phase, so it's the same. So we just changed the double sharing here generation. So then the online is 2 elements in both cases. Okay. So that was the first improvement to the Dam-Korniasa protocol. And now I'm going to show you how we can actually reduce the round complexity. So this information theoretic protocols, we have to communicate per multiplication gate, okay? And in fact, like the number of rounds is proportional to the depth of the circuit. So it's a big open problem to reduce like this communication complexity. It's not even like known if you can actually do it in constant round. The results are there, so that it's probably impossible. So any improvement to the round complexity is significant here. So here we have this idea where we reduce the round complexity by 2. So let's say we have like the circuit here. So basically what we do, let's imagine we have the circuit. So in the odd layers, basically we are able to compress them with the previous with the even layers. Okay, so think that we can run with no interaction 2 layers together. Okay, and if we want to achieve that, let's say here is the first layer and here is the second layer. If we want to achieve this, then we need basically, if we want to do it non-interactively, to calculate the second layer gate, we need to know the inputs of the previous one, right? And this is the difficulty here. So before going back to show how we can solve this, let's recall Beaver triples. I mean, I didn't watch all the talks in the workshop, but I'm sure that somebody talked about this. So why doesn't it move now? Okay. So I assume that you're familiar with Beaver triples. So what we can do if we have these public values, then if the parties have values of the form u minus a and v minus b, so here are the Beaver triples, okay? Then we can actually operate on the shares, okay? So this is how you can basically, given the shares of the Beaver triples, you are able to communicate and do multiplications. Okay, so I'm assuming that you're all familiar with this. Okay, and here what I want to get that will be useful in the previous, in the next slide, is that here what we really want and emphasize is that pay attention to how the sharings need to look like. Okay, so you need to have u like a value, like some input value minus this sharing that you can have in the preprocessing. Okay? So now, given this, as we saw with the Beaver tuples, we can calculate if the inputs are of this form, then we can use Beaver tuples to do the multiplication with no interaction. Okay. This is what I just said. Okay, so now if the outputs of the first layer are of this form, u minus a, then given this observation, we can actually calculate the second layer gates with no interaction. Okay? So if the first layer outputs values like that, then we can just directly apply what I just told you. And in fact, this is great because if you remember what I showed you in the DN protocol, the outputs of the previous gates, they really look like that. Okay, so let's go back here and see. So if you remember, this is the protocol. And what was happening here, we were like sending the shares to the king, and then the king was basically reconstructing, and then we were subtracting this double sharing. Okay, so if you see, so this is the local calculation. So this is the u value that comes out from the previous gate, and this is the a value. Okay, so this protocol already has this format that we can use. So what we can do now, so here is how we are gonna execute the protocol. So we start with the Beaver tuples, okay, and then we run the first layer multiplication, we receive the outputs, and then we can actually execute, we can execute the third multiplication using the Beaver tuples. Okay, so this is the observation that we get here, and in this way you can actually evaluate both layers kind of at once, and you can reduce the round complexity by half. Okay, and here just I want to say that we cannot really pre-process this these Beaver tuples because they depend on the input. Okay, so we do it in parallel. So basically, when we're evaluating this gate, we can also prepare the Beaver tuples for the next layer. Okay, so this is how we are doing it. So in the odd layers, basically we need to use the original DN protocol to get this nice property in the format of the output. And then in the even layers, we use the new protocol that I showed you earlier, the one that we use the T-wise independency. So following now this approach, we can actually reduce it down to 5 elements, right? So it's like 6 plus 4 for these two protocols, and then we divide by half, and we end up with 5 elements. Okay. And here, if we want to actually combine, oh, that was the T-wise. Okay, so this was the very, I got confused, guys. So this is the original DN protocol, and this is the one with the T-wise. So with the T-wise, we have the 4.5 elements. Okay. So here is the complexity that we just have like in total for the DN protocol. It's basically 4 times size of the circle times n. Okay. And we can also reduce the depth by half. Okay. And this is basically what we can have for honest majority. So this is like the best complexities that we currently have. So what's next? So now in the online phase of these protocols that I just saw you in this family of protocols, the communication complexity is linear in n. Okay, so what we would like to do is basically get rid of this n. So it would be nice to have a protocol where the online computation doesn't depend on n. So this is what we will try to solve now. And we will just focus on the online phase. So basically we will try to see, we achieved these results for Atlas. So now we're trying to see if we can reduce further the online complexity. So we focus on applications where you want to optimize the online complexity. I will also talk about how much the preprocessing has to be. So, so we are going to achieve this result without increasing a lot the preprocessing. I'm going to give you the numbers. Okay, and here are the previous works. So if we have honest majority, as I was saying before, like the previous protocols in Atlas, so we need communication complexity, which is linear in n. And if we actually consider a slightly suboptimal threshold, based on all these works that they use packed secret sharing, then we can actually get communication which is not linear in n. Okay, and there is this recent work that basically achieves the result, but it achieves it for like circuits that have a specific structure. And then what Vipul showed you, he showed you a protocol with these sharing transformations where we can actually achieve communication complexity, which is not linear in n. Okay, so this is the result that Vipul showed. So in that result, we are able to achieve MPC with order of C communication. And again, so this is again for the suboptimal threshold. Okay, so and that work actually also extends to the honest majority setting, to like to the strict honest majority setting. So let me say it more clearly here. So we have the previous, so this is the work that Vipul showed. So here we get actually communication complexity, which is proportional to the circuit size. And in this previous work, we actually also got it for the suboptimal threshold. And for the honest majority, as you can see, for the strict honest majority, we didn't know this before. So with the setting transformations, we are able to achieve this linear actually independence of the number of parties. Okay, so now we are focusing on this work that we have here. And we're gonna try to improve the online complexity. And in particular, like really care about the constant. So this work here is only like, I'll show you the numbers. It's like, we could call it that it's only asymptotically efficient. And we provide a simpler solution to that too. So we're gonna compare the constants and also see the new construction, which is simpler and avoids basically permutations. If you remember from Vipul's talk, he was showing how you can use setting transformation to like do many linear operations, such as, for example, permutations. So in this work, we are going to avoid this step and have a simple protocol. Okay, so this is again the setting transformation paper that we have that has only the asymptotic efficiencies.
Antigoni,
Yes.
we have slight technical problems here.
Oh, what?
We're trying to move the presentation from one laptop to another because somehow Zoom crashed on our side.
Oh, okay.
All good. Just a moment.
Do you want me to go back?
No, we just crashed like right now. So we'll be there in no time. No pressure, I will.
Okay, just let me know.
One moment. And we're back online.
Okay. So I will just repeat this slide. So now our goal is to have an online phase, which is much faster than the online phase that we can achieve using the sharing transformations work. So this is the goal now. And let's compare them explicitly. So we call the new work TurboPack. And we call it TurboPack because you will see that it borrows some idea from turbo speeds. That's why we call it TurboPack, and we are using pack secret sharing. And this is the work with Daniel Escudero, Vipul, myself, and Ethan. So let's see the explicit constants here. So, and as I was saying, we're trying to improve the online phase. And in this case, we don't have the dependency on the number of parties in the online phase. So our final result here is going to be 12 elements in the online phase. And we have two pre-processing phases. So there's a pre-processing phase, which can be circuit independent. And in that case, that complexity will be 10n plus 24. And then we can have another pre-processing phase, which is input circuit dependent, function dependent, which is 8 elements, okay? So if we're not happy with the circuit dependent pre-processing, then we can actually transfer these 8 elements to the online phase, and then it will be 20 elements, okay? So this is the results that we are achieving in this work. And if you want to compare with the setting transformations paper, here we had like 108 elements. So you can see here there's a big difference. And again, like these things use packed secret sharing. Okay. So here is like the complexities n over k, where k is like that we packed k secrets in one sharing. And for the offline phase, we have so many elements. Actually, I think it's 192 elements here. Yeah. So these are the improvements that we get over the paper that does the sharing transformation. And apart from these improvements on the number of elements exchanged, as I was saying, we also have a conceptually simpler solution. So let me go over that solution. So we use packed secret sharing, where instead of hiding one secret in one sharing, we hide many. And here, basically now we can have gates where we can patch k values. Okay, so we can have like this SND circuit. And the benefit is that now you operate on the shares at once. And we don't need to go over all of these details. So here, what I want to say is that when the number of shares is order of n, then the total cost of operating on this is basically order of c. Okay, so we don't have the dependency on the number of parties. Okay, and here is explicitly. So given that you have k copies, then for the multiplication gate, you pay n over k, and then the overall cost is like you need to multiply by the circuit size. Okay, so again, given that k is order of n. Okay, so an issue that appears when you want to use this type of sharings is basically the ordering here. So input shares like can come from different locations here. for different sharings, and even in the same sharing, you also need like different reordering. Okay, for example, here the output sharing in the last layer is this, but we need the input sharing to be basically, we need to reorder. Okay, so you need to take care of all of that, and we can use the sharing transformations and network routing and all of these techniques. And this is if you have like settings in different locations. So we're going to like avoid these problems, and we're going to use a king again. So we're going to have a designated party, and the high-level idea here is that we are sending some information to this party, and this information allows this party to basically reorder the shares by itself. Okay, so now we don't need to apply these permutation operations over like the shares. So we are sending some information to P1 that allows him to do locally these computations for the routing. Think of it like that. Okay, and that basically allows us to like not use all this fancy permutation techniques that we had before. So let me tell you what is this information that P1 is receiving to allow us to do that. So we are using the following setting. So let's say we have a multiplication gate with wires A, alpha, beta, and gamma. So we are assigning a random value to every wire. So for the A, we are assigning the value LA, lambda, sorry, I'm Greek. When I say lambda, I say L, I don't know why. So lambda A. So for the wire A, we give the random value lambda A, for B, lambda B, and for gamma, lambda gamma, okay? And we have the relation that basically lambda gamma is equal to the summation of the other lambdas, okay? And also, let's say for now that the parties, they're gonna have like sharings of the following values, lambda alpha, lambda beta, and lambda alpha times lambda beta minus lambda gamma over this sharings of these degrees, okay? I mean, you will see later why the degrees are like that, but assume that we have that in the pre-processing phase. So in the pre-processing phase, we just need to generate these values where the lambdas are random values associated with every wire. Okay, and we want to maintain the invariant to be able to have like P1 to do this reordering, to be able to operate on packet secret sharing. We have the invariant that, let's say UA is the real value of the circuit. So every time that P1 calculates, we want to maintain the invariant that MA is basically UA minus lambda A, okay? So this is how we're going to use the lambda A in our online phase. So the moment that we keep this invariant, then we can calculate on this M values, and then we can get the result. And in that case, basically the UA, the real values in the online phase, they will never get like secret share. So we will not need to work on secret share values of the input. We will have to work on secret share values of the values that we generate in the pre-processing phase. And there was a work from Ben Hamoud et al. In 2021 that they used also like this similar setup from turbo speeds. However, their work is not for the strict honest majority. They are in the suboptimal threshold, and we need to change their work to work in the honest majority. So we are using different techniques. Okay, so how are we going to maintain this invariant? So for the input gates, it's very easy. Okay, so every part has as input, let's say UA, and then the input that they send to the king is basically UA minus lambda A. Okay, and every party that holds a wire A, they also hold the wire lambda A in the clear, so they can perfectly calculate this M value here. Actually, this is called mi in Greek, not mu. But I'm going to call it me. Okay. So for the addition gates, again, if we have the invariant that the previous the previous outputs of the previous gates are at this form. So now if we have an addition gate, we can basically add locally the mi alpha and the mi beta, and then you can get the mi gamma. Okay, so everything is linear here, and this can be done locally. Okay, so basically here you will get the result of u gamma will be ua plus u beta. Okay. So now let's go to the multiplication gates, which is slightly more complicated. This is the biggest equation I have in this presentation, so just bear with me. So what is the goal here? So the goal is to basically keep the invariant that after we do a multiplication, we end up with ua times ub. Again, alpha and beta, I'm confusing these values, okay? I hope you understand. Okay, so u alpha times u beta minus lambda gamma. Okay, so this is the goal. That's what we want to have to maintain the invariant and be able to operate and evaluate the circuit. Okay, and let's say from the previous gate we are getting MA, M alpha, and M beta, which they already follow the invariant. Okay, so what we can do, so remember, the king is supposed to have these values from the previous layers. So then what the king does, he basically generates a secret sharing of mi alpha and mi beta with degree k minus 1. Okay, and this is what it sends to all the other parties. Okay, so now all the other parties, remember, we also have the pre-processing. So if you remember in the previous slide here, this is the pre-processing that we assume that we already have these values. I'm going to show you in the last slide how to generate this, but in the online phase, assume that we already have these shares here. Okay, so what PJ can do, in fact, locally to calculate the M gamma. So it can take the shares that it received from P1. Okay, and then based on the pre-processed data that it has, it can calculate the rest of this expression. Okay, so why is this expression like that? So you can see it from here. Okay, so we want to compute mi gamma, right? Which is basically ua times u beta minus lambda gamma. And every u is ma plus lambda a, okay? So if we actually replace in this sharing these values, and then if we multiply here, we get ma times m beta, which is the term that we have here at the front. Then we have the term ma times L beta, so you can find all the terms here. So everything is done locally. So the parties have these shares which are generated in the pre-processing phase, and they also received these values, ma, m alpha, and m beta from the king. Okay. And again, so here, I mean, you can see what's going on with the degree. So this pack secret sharing is what we also call multiplication friendly. So when we are executing and multiplying values with these degrees, we are getting like sharing of degree t plus 2k minus 1. Okay. So this is the online phase. So as you can see, it's kind of like very non-interactive. The parties just talk to the king once, sending the shares, and the P1 reconstructs, and then reshares again and sends this mi shares to the parties, and then the parties completely locally, they can generate M gamma, which is the invariant for the next gate. Okay, so this is the online phase, nothing else is happening in the online phase. Okay. And if we count the number of elements that we need to exchange here is 12, as I showed you earlier. Okay, so now I'm going to show you how we can generate this pre-processed data. How much time do I have, Karsten? Like, do I have like 5 minutes?
Let's say 10 minutes more.
Oh, okay. Okay, good. I think it would be faster. Let's see. Okay. So let me show you how we can generate the pre-processing phase. Okay. So we're going to use Beaver triples in the packed secret sharing form. So assuming that we have these Beaver triples, okay, for values A, B, and C, So actually here it can be confusing because I have both A and alpha values. So we have this Beaver triples of the corresponding degrees. And we also gonna have another sharing that we're going to generate. So this is going to be basically the pre-processing phase, which is independent of the circuit. Okay. And we're going to have another sharing where basically here in this sharing, it means that we have k copies of the value lambda alpha. Okay, this is what it means here. So let's see how we can generate now this pre-processed values. I'm talking about these values here, the lambda A, lambda B. Okay. So every party, they can actually now, here we have this multiplication friendliness of the pack secret sharing. So basically, if you get the lambda values and then you actually multiply with a sharing where this is actually the vector where it has like 1 in location I, everywhere else is 0. So if we do this, and here is the sum for overall the case. If we multiply this, then we're going to get a new sharing where the degree is actually consistent with the degree of the final sharing that we want to achieve. So this is the goal, okay? So I want to show how we can generate lambda alpha times lambda beta minus lambda gamma in this sharing here. Okay. So as a first step, every party does this for actually lambda alpha and lambda beta. I didn't write the equation for the lambda beta. And then what happens is that the parties send these sharings to the king. And then the king, he can actually reconstruct these values. So remember, like here we also have, oops. So here we also have these sharings. So it can basically reconstruct, and then he can redistribute LA minus A under the new degree, K minus 1. Okay. And now what we can do, again, we do this for both, here I should have a comma. We do it for both LA minus A and LB minus B. And then this is the values that we send to PJ. So now every PJ, we can actually now get rid of this value A, okay? So since we have the Beaver tuple from here, we can actually get rid of the A, and we end up with lambda alpha of this degree, and also lambda beta. Again, I didn't add the equation for the lambda beta. And then basically, once you have lambda alpha under this degree and lambda beta under this degree, I mean, you can use any multiplication protocol to get that, okay? I'm not gonna like open up here the equation to show you even more equations on how to generate this degree, this sharing, but think that you can use any multiplication here to get this result, okay? So this is the process on how we can generate the lambda values. And then how to generate the Beaver triples. I don't have it on the slide, but we are also like generating these sharings because they're packed sharings, so we have to accommodate for that. Okay, but I'm not going to show you in this talk how to generate those sharings. Okay. So that was the circuit dependent preprocessing phase, and here I'm bringing back the same slide with the complexities. So now, as you can see, if we want to compare what we have achieved here, this is the number of elements that we have, but now actually we should also compare with the Atlas and the DN protocol, how much is the improvement there, because if you remember, there the online phase grows linear with the number of parties n, okay? So if n is small, then maybe that protocol is also faster, right? So for this DN and Atlas, the preprocessing was actually 4n elements. So our preprocessing, as you can see, is slightly bigger. Okay. And then the online phase, the most optimized that you can get, if you only want to focus optimizing the online complexity of these previous protocols, the Atlas and the DN, you can get 1.5 n elements in the online phase. And as you can see there, like for smaller values of n, that can be faster, but as we get more parties then TurboPack starts kicking in, okay? And in the experiments, we saw that you don't need like a lot of parties, like less than 20 parties, basically, to start seeing improvements. Okay, and I'm not gonna show you the running times, but I wanna mention that we have implemented our result in this library of Anas. I think he's there. So this is a library that it doesn't have like any dependencies, it's self-contained. So you can have a look. And now like, yeah, I can talk about some open problems. So here we saw how we can have an online phase, which is basically independent of N, and it can be very fast. And we also simplified the protocol. We don't use this machinery for like routing, which I didn't show you how the old machinery looks like, but it's fairly complicated. So now we want to ask the question if we can improve the total communication complexity of the protocol. So for example, here, what is the total communication complexity? It's going to be like 10n plus 44 elements. Is it 20? Yeah, right. So now the question is if we want to improve in total the communication complexity of this information theoretic protocols, we can actually see if we can get something better also in the pre-processing phase. So I would like to leave this as an open problem. And thank you. Let me know if you have any questions.
So, are there questions for Antigoni? Ivan, yeah?
It didn't become clear to me why you need to compare this protocol, which is the dishonest majority, to atoms, which is the honest majority. I mean, if you had dishonest majority, then the honest majority protocols will not work.
Okay, you heard that, Antigoni?
No, is it Ivan asking why we're not comparing TurboPack to the dishonest majority? Can you?
I thought I heard you say that you wanted to compare TurboPack to atoms. And that is an honest majority protocol, right?
Right, yeah.
So why would you, I mean, if you assume a dishonest majority, then you cannot run atoms, right?
Yeah, so, okay, so this is, the TurboPack is only for honest majority, okay?
Yeah, the threshold there is for honest majority, right?
Yes, so everything is for honest majority. So when K is n over 4 is for honest majority. So everything that we built for TurboPack is in the honest majority case. So we could extend to the dishonest majority case. For example, let's say to try and beat the online phase of speeds, for example. However, like doing some calculations, we will need to have like more than 100 parties with the current technique to beat also like the results in the dishonest majority case. But everything that I showed here is for the honest majority case. Does this answer the question? Because I don't hear Ivan very well.
I can say what Ivan said. If what's your?
No, but I mean, but asymptotically, it's still, I mean, TurboPack still improves.
Yeah, so Ivan asked if TurboPack asymptotically improves over speeds.
Oh, if asymptotically for the online phase. No, it doesn't. So we cannot improve it asymptotically. I mean, we can actually, it does for the, so the sharing transformation paper did this already, okay? So this work, the GPS, it did improve. So for this threshold where we have the suboptimal for dishonest majority, there we do actually get rid of the linear dependency. So we inherit all the asymptotic complexities of this linear transformation paper. And we just optimize here only for the honest majority. So yeah, in the sense it does, yeah.
Okay, I think Ivan is satisfied now.
Okay. Carsten, if people have questions, if you can repeat them or give them the microphone, is it possible to?
I will mention if there are more questions. If not, then I for sure have at least one. So this whole thing only works with passive security, right?
Yeah, everything that I showed you here is passive security, but we also saw how we can achieve malicious security. So we also have in the same protocol how we can achieve malicious security. So we do like, I mean, I don't have time to say all the details, but basically we try to reduce everything to inner product verifications. So that's what we're trying to do, and then we just run these verifications, like very similar to the previous works, but we have to adopt it to this setting.
Okay, and one teeny tiny question at the end also from me, which is it wasn't exactly clear for me where you get rid of the problem of the routing, of like moving stuff around within the secret sharings. Maybe I just have missed that. Is it because you reconstruct to one party and that party then does the job for you?
Exactly, yeah. So P1 here, right? So we have this invariant, right? That P1, he does the reconstruction.
The processing already contains what you want, and then P1 just extracts and moves things around.
Exactly, so he can do the job, yes.
Gotcha, thanks. More questions? Otherwise, please, loud round of applause so Antigoni can hear us.